Okay, so last class, we very briefly at the end, in the middle of a proof, I said this sequence is not convergent. It was a sequence where all the elements were like distance 1 from each other. So it was a sequence, it was like the sequence, all zeros and then a 1 in the nth entry, and those are all distance 1 from each other. So you can kind of think of that kind of example. And we said if they're all distance 1 from each other, there's no way they can converge. Because whatever they converge to, if they all get really close to that, then they have to be close to each other. So this idea of being really close to each other, it is called a Cauchy sequence, and that is the next little topic we're doing. And here's the precise definition of a Cauchy sequence. The framework is that we're in a normed vector space, as always. So we have a vector space, and we have the norm, and the Cauchy sequences are the ones where the norms between the elements in the sequence gets really small. So xn minus xm, that will shrink down and become arbitrarily small, less than epsilon. And the way it works is for every epsilon greater than 0, eventually, so there's some big capital N, eventually everything after that capital N is all close together. So I really think of these as sequences that get close together. I'm sure we could come up with a better name than Cauchy sequence. Of course, Cauchy was some French mathematician, and I guess it got named after him. It should be called like the close together sequences, right? On the other hand, we've already talked a lot about, and of course, like a lot of your math career is talking about convergent sequences, which are sequences that get close to one particular element, right? And these two ideas are related. So Cauchy, close together, the xn's are close to themselves. Convergent, they're all close to one single other point, right? The limit of xn equals x. And last time we basically proved if it's convergent, then it's Cauchy. And we actually did it the other way. We said if it's not Cauchy, then it's not convergent. That's the contrapositive. I'll give you also a direct proof now. It's very simple. If it's convergent, then it's Cauchy. And then the big question today, or one of the big questions for today, is the reverse true. If it's Cauchy, then is it convergent, right? So one way is definitely true. Is the other way true? Okay, think for a few minutes and decide.
I was going to say something because I think it was real close.
Yeah, I was thinking more like
So it is like,
kind of travel as a buddies.
so you mean,
Like they can get close.
Yeah.
so you mean like just convergence in general, like if I had a bunch of sequence of rationals, it didn't matter if you converged to irrational, it was
You have
still
like pairs.
So I think that you should think of it as you're in
Yeah,
a
I was
normed
saying
vector space. And the only things you know are like the axioms of a normed vector space. So you know you can add things, you know you can take norms, like you know the norm-based triangle inequality, that kind of thing. But you don't know anything else about space. So is it yeah. So I mean, as soon as you have vectors and you have a norm, you can ask if a sequence is Cauchy. You can ask if a sequence is convergent, and it makes sense to ask this question.
I think what you just said is right. It's like if a sequence goes like this, and then there's some like this, but then over here.
Yeah.
Oh wait, no, because then you can't drop all around here because of this gap, because those have to be. I agree with the sentiment. I just don't know.
The other two I'm gonna say was my opposite is that like if you're going through every point, like eventually you'll find a point that it is closest to, and that'll show, right? Like you'll have to cross it.
Okay, so there's like 40 seconds. Put in a guess. Of course, it's quite. This is one of those questions where I think at this point unless you've seen this before, you won't know the answer. But we just want you to think about it before I tell you the answer. Okay. Well, there's 10 people in the room, and there's 10 answers. So let's stop 20 seconds early and see what people said. Okay. 8 people said no, 2 people said yes. And what did I put as the correct answer? I put in both as the correct answer. Why is it both? I mean, okay, very technically speaking, no is the correct answer. So if you selected no, that is like the technically correct, the answer to this question is technically no. But the thing is, the answer in real problems, when you really work on actual things you care about, like actual functions and things, the answer will be yes. So what do I mean by that? I mean, if the space is nice, then the answer is yes. If the space is not nice, then the answer could be no. Okay? And we give this nice thing a name. It has a name. It's called complete. So not only is it a fancy name, let's go to our little note thing. And I guess I have to open it. let me find the little note thing. Okay, it's not open. That's why I can't find it. Okay, so this is the little map, and this is the definition we're starting with today. The definition, normed vector space, that's what we've been doing so far, is called complete if every Cauchy sequence converges. So if you're in a complete space, then the answer is yes. Of course, not every space is complete. Some spaces are not complete. And this has a name. This is definition 1.4.5. Let me also write down the definition of a Cauchy sequence so that this makes more sense. Definition 1.4.1 is a Cauchy sequence. And I think of this as points get close to each other. Points get close to each other is for all epsilon greater than 0 exists n such that for all nm greater than n, the norm of xn minus xm is less than epsilon. So the points get close to themselves, and it's called complete if every Cauchy sequence converges. So when you're in a complete space, the answer is yes. If you're in a not complete space, the answer is possibly no. Let's do a couple little examples. And first, before we do an example, let me show you like a little picture just to get things going. Why is it called complete? Complete is actually a good name in this case. So a lot of math has bad names, but complete is a good name. So let's draw a picture of this stuff. So let's say we have these points. Here's x1, here's x2, here's x3, here's x4. What does convergent mean? Convergent means there's some final limit, which is like x, and you get really close to x. What do I mean by really close to x? Whatever little ball you draw around x, eventually the sequence is within the ball. That's convergent. And Cauchy means that if you draw a little ball around the points are within the little ball of themselves. Okay? And okay, here is one easy proof. Let's do a quick easy proof. And here's the easy proof that convergent implies Cauchy, which we also did last time using the contrapositive, but let's do it directly this time. If it's convergent, then it's Cauchy. And the basic idea is, okay, well, if you're within epsilon of the limit point x, then eventually all the points live in this little circle, right? So eventually, except for the first finitely many terms of the sequence, all of the terms are inside a ball of radius epsilon of x. But if they're in a ball of radius epsilon from x, they can be at most epsilon over 2 from each other, right? Or I guess 2 epsilon, right? Like worst case scenario, one of them is on this side, like here's x100, and here's x101. If they're both within epsilon of x, then they're at most 2 epsilon apart, right? But this holds for any epsilon. Okay, so let's take this picture proof. They were eventually inside the ball of radius epsilon from x, and therefore they're within 2 epsilon of each other. Let's turn that into a little proof by writing it down. So we have the picture, let's write it down. So if limit as n goes to infinity of xn equals x, then for all epsilon greater than 0, there exists n, so norm of xn minus x is less than epsilon for all n greater than n. And actually, we know that we know that whatever we get at the end is going to be double as much. So why don't we do the really slick thing, and we'll put an epsilon by 2 now, and then our epsilon by 2, when it gets doubled, will turn into epsilon, and then we'll have like completed the proof. So xn minus x is less than epsilon over 2. Eventually, you're inside that like little yellow spot around the point x. But then, for all nm greater than n, we have the norm of xn minus xm is less than what? Well, this is just like the points x100 and x101, right? If they're both in the ball, and you're both within epsilon of x, then you're going to be within 2 epsilon of each other. In this case, it's just by triangle inequality. So less than xn minus x plus xm minus x. And that is less than epsilon over 2 plus epsilon over 2. Okay, I guess strictly less than to be fancy. Okay, which is epsilon. And that is the definition of Cauchy. So there we go. So if they're converging, then if they're all getting close to x, then of course they're getting close to each other. Okay. That's the easy way. And now let's talk about completeness. So what would not complete mean? You'd have a sequence where the things are getting close to each other, but somehow the limit doesn't exist. And you really should think of what's going on is there is some kind of hole in the space. That's what's going on. So do Cauchy sequences converge? And the only possible way they might not is yes, unless there's holes. Unless there are holes. Okay, and to give you another example of a picture proof, if you have x1 and x2, imagine they're getting very close together, x4. So they're all getting close to each other. They're kind of bunching up all together. Maybe they bunch up all together, but then there's like a big fat hole right here. And they kind of like bunch up really close to that hole. And so there's no final thing that they're getting close to. They're all just getting closer and closer to that hole. And that would be a situation where it doesn't converge. So that's what I mean by a hole. And the property of being complete is really saying complete is really means no holes. No holes. Let's do some sort of concrete examples. This will be a good one. Can anyone think of a space that does have a hole? Yeah.
Rational?
Yeah, the rational numbers are famous for having holes. So a really good example of a not complete space. Let's do an example of a not complete space is the rationals, Q. And so for example, if you look at the set of x such that x squared is less than 2, okay, let's not call them x, let's call them q, so we know they're rationals, we make sure we remember. Q such that q squared is less than 2, this is a subset of the rationals. All the rational numbers that have the property that when you square them, it's less than 2. This is something that you can easily do, right? You can square a rational number, you can see if it's 2, or bigger or less than 2, you just compare the numerator and the denominator, right? So a very valid thing that any like fourth grader can do is check if a rational number squared is less than 2. But if you look at the space, you can make a sequence in the space that doesn't converge to anything, right? In Q. And the reason is you can have a sequence x1, x2, x3, and they're getting closer and closer. They're all kind of like bunching up against the limit of the largest possible value in the set. So you could say that you take the biggest thing that's in the set, make them bigger and bigger and bigger forever, and it's getting closer and closer to something. That something is the square root of 2. But square root of 2 is famously not a rational number, so this set has sequences that don't converge to anything. They just get closer and closer to the square root of 2. And they're Cauchy sequences, they get closer and closer together. They would be convergent if we were working in R, but they're not convergent in Q. So I think that's like the best example of a not complete space. And a good example of a complete space is R. A complete space is R. So R is basically you take Q. If you take Q and you fix all the holes, you sort of like take the holes and you add in numbers. You say anytime I had a sequence of rational numbers that had no limit, a Cauchy sequence of rational numbers that had no limit, I add that in as a new number. That is how you get R. And so it's almost like an axiom for us in this course, like that it's complete space sort of by fiat. It's the set of things that you get by completing Q. This is, by the way, this is done kind of somewhat formally in the textbook if you want to read it. I believe I wrote down the page number. Where did I write down the page number? Page 24. So see page 24 for one way to define R. So on page 24 in the textbook, they tell you what it means to do the completion of a space. So you start with a space with holes, and it tells you how to fix it by adding in all the holes. It ends up being kind of ugly, but that is kind of how one way to make R. And R by fiat is a complete space. All of the Cauchy sequences in R converge, because if it didn't converge, we would just add a new number there and say that's the number. Okay, great example. Questions or comments about any of that? We did do another nice example we did last class of a not complete space, and I'll give you another good example of how they come up in sort of real life. Like you might think this QR thing is a little bit silly, but they come up in function spaces as well. The space of polynomials on 0, 1 is a not complete space. Why is the space of polynomials not complete space? We saw last time you can have a sequence of polynomials that converges to the exponential function. That sequence of polynomials, that was the sequence xn. Did I call it? I probably called it Pn, P for polynomial. That was the sequence Pn, which is the sum from k equals 0 to n of x to the k over k factorial. That's Pn of x. So this sequence is a Cauchy sequence, and it converges in the space of all continuous functions to the exponential function. And you can check that how far apart they are is sort of like the tails of the sequence, which are totally fine because the 1 over k factorial is shrinking things so fast. So this is definitely Cauchy, but it doesn't converge to a polynomial. Cauchy, but limit is not a polynomial. And that shows that the space of polynomials is not a complete space. So when you have function spaces, it's kind of like an open question sometimes. Is it going to be complete or not? And all the nice ones that you want to work in are, but sometimes it's like a little bit of work to prove that it is. Okay, so that was from last time. Let's go back to the little important definitions. When a normed vector space, when it's complete, we give it a special name. And that name is a Banach space. A Banach space. So this is called a Banach space. So Banach was some famous mathematician from the 1900s. I guess it's a silly name. Like we could have just said complete normed spaces, but like Cauchy sequence, we named it after some guy. I will say there is exactly one thing I like about the space or the name Banach space. And it is the following joke, which is one of my favorite math jokes. And it's so important, I'm going to write it down on the overrule. Okay, so you ready for the joke? The joke. What is yellow, normed, and complete? What is yellow, normed, and complete? Bananach space. Bananach space. Okay. That's one of my favorite jokes. I got a couple more like this. When we get to them, I will let you know. Okay. And now you will never forget. Okay, so what do we have? Cauchy convergent, a Banach space, if the limit exists. Okay. Polynomials. Okay, so the thing we're about to do is a nice example, 1.4.7, and I'm going to prove that the space of continuous functions is a Banach space. So CC of 0, 1, this is continuous functions on 0, 1 with the uniform norm. With the uniform norm is a Banach space. And we've already shown that it's a normed vector space. We just have to prove that it's complete. So more specifically, I'm just going to prove it's complete. That's what I'm about to do. The proof is not too bad, but we are going to get into like a messy proof. This is a good place to stop if there's a question before we get halfway through the messy proof. Yeah?
For the sequence that you gave in the rational numbers that goes towards root 2.
Yes, let me find it. Where is my thing? Okay, here. Yeah.
So in my head, I'm trying to sort of compare the difference between completeness and being closed. And
yes.
In this case, it simply doesn't converge, so it's not that Q doesn't contain the limit point, it's just that the sequence doesn't technically converge in Q.
Yeah, so okay, so this is the only difference between closed and complete really is what is in the space and what is not in the space. Okay, so like a good way of saying it is the set Q squared less than 2 is not a closed subset of R, right? That's what if we were living in R and we were like R people and everything was a real number, then we would just say, oh, the reason it's not converging, it converges to something, but it just like escaped the set you were in, and we would say that means not closed.
I see.
But if we are Q people and the only thing we know about are rational numbers, we can still measure the distance between rational numbers, and we can still say, hey, this is a Cauchy sequence. I can see that the points are getting really close to themselves. But there is no limit. And then we would say, that means that the space is not complete. So it is kind of a point of view. And I guess if you take a closed subset of a complete space, it's still complete. This is like the exercise version of what you said. So I'll leave this as an exercise. It's not hard. A closed subset of a complete space is still complete. Is still complete. Okay. Oh, okay, so if you take a subset of a space, it might not be a space anymore, right? Because part of what we said for being a normed space is it has to be closed under vector addition. If you have a subset that is also a space, people call this a subspace. So it should say a subspace. A closed subspace of a complete space is still complete. And I think this one is even in the textbook. I kind of remember seeing this. I don't remember what the exercise is, but somewhere in C 1.4, somewhere in 1.4, this exercise will appear. Okay, yeah, fantastic question. Anyone else? Yeah.
What's the norm with infinity?
Oh yeah, right. So we're going to do this proof. I will remind you what the norm infinity is. The norm infinity is the uniform norm. The norm of f infinity is the sup norm, the sup of f of x. And we're working on 0, 1, so that's what it is. So this is for C of 0, 1 with norm. So some people call this the infinity norm. Some people call it the uniform norm. And the point is that if the uniform norm is getting small, like if the norm is less than epsilon, then the absolute value of the function has to be less than epsilon everywhere. That's why it's like uniform. It's everywhere the same thing. It's always less than epsilon. This is in contrast to things like the L1 norm and stuff, where you can be, on average, you're sort of less than epsilon, but you might have these like spikes where it's very bad. As long as the spikes are very small, then it's okay. And we're going to see more of those later, but for now, the uniform norm. Okay, so this is exercise, or example, 1.4.7 in the textbook, that this space we will prove is complete. That's what we're proving. Okay, so you guys ready for the proof then? Okay, so what do we have? We're given a Cauchy sequence, and we got to find some limit and prove that the limit is still a function that is a continuous function. So let Fn be a Cauchy sequence, and Cauchy with respect to, if you want a reminder, with respect to infinity norm, right? So the functions, they get close together if you measure them in the infinity norm. And this is the nice thing about the uniform norm. If the functions are Cauchy with respect to the infinity norm, then for every x, it's going to be Cauchy. So for every x in 0, 1, if you look at the sequence Fn of x, I claim this is Cauchy in R. This is Cauchy in R. And we could do a little because. We could say because the absolute value of Fn of x minus Fm of x is less than or equal to, I guess, the norm of Fn minus Fm, right? So if you look at the sequence of functions, you're measuring how close they are with respect to this norm, and we know they're Cauchy, so they eventually get less than epsilon. Well, then for every individual point that you look at, it's going to be a Cauchy sequence in R, because you measure, how do you measure Cauchy sequences in R with respect to the absolute value function? The absolute value function, I'll write it like that. So the absolute value function is like measuring how far apart things are in R, and if it's a Cauchy sequence of functions with respect to the norm, then these numbers are Cauchy sequences. So it's a Cauchy sequence in R. So this is the really nice thing about the uniform norm, and why it's like such a nice norm, is basically it takes properties about the functions and it applies them to every single point uniformly that you have. And so we definitely have pointwise convergence. Question here, yeah.
This might be a totally stupid question.
Yeah.
But, could you also similarly say that because it's Cauchy in R and you're taking a closed subspace, that space had the 0 to 1 has all the limits, like all the points that it could possibly converge to in that closed?
Okay. Maybe I'm not quite sure if I understand your question. I guess there's two things. So there's 0 to 1, which is like the x value.
Yeah.
And then this in R is sort of like the y values.
Mm-hmm.
So I'm talking about the sequence Fn of x. So for some fixed x, like let's say 0.5, Fn of 0.5 is a sequence in R, and I'm claiming it's a Cauchy sequence in R because it's bounded by this. Did that? Yeah.
Yeah. Okay.
Did that answer your question? I'm not
I
quite
think
sure.
so.
Okay. So for every single x, it's a Cauchy sequence. Because R is complete, that was the example I gave you. Why is R complete? R being complete is sort of like an axiom of the space R. So, and in fact, every time there's a complete space somewhere in this course, if you dig deeply enough, it's eventually going to come down to the reason it's complete is because R is complete, and we put some layers on top. And that's where we're going to use this here. So R is complete, since R is complete, right? This is by axiom, essentially, by axioms of R. Therefore, Fn of x converges to something. So the limit as n goes to infinity of Fn of x, it's something. Let's call that thing f of x, the limit. So we'll call that f of x. Okay. So we're converging to some f of x. Oh, okay. This is great. So there's a couple things we still got to do. We're not done the proof yet. You might think we're done. There's actually a couple things we got to do. I have one of the things written down. There's another one that occurred to me that I did not write down. So we're going to have fun of discovering it right now. But can someone tell me why we're not done? Like, if I just finish the proof now, why are we not finished? Like, you gave me a Cauchy sequence, I gave you the limit. It's the function f. What's the problem? Yeah.
You have proven that f of x is actually continuous.
Yes, okay, this is one thing. So this is one problem. So we're not done yet. Not done yet. Fantastic point. Not done yet. So issue number one. Issue number one. Is f even continuous? Right? So it could just be like the polynomials where it converges to something, but the something is not a polynomial, and then our space wouldn't be complete. So this is definitely an issue, and this is the one I have the answer for. So this one we're good on. But there's actually another issue that I realized, and it's probably silly. There's probably some super simple argument. I'll let you guys think for a sec. Yeah, I wrote down, the next thing I have in my notes is the proof that f is continuous. But there's this other fact, and I use it in the proof, so we got to do that other fact first. Okay, I'll let you guys think about it while I look at the textbook and find out how to solve this issue. Oh, okay, great. Yeah, okay. There's exactly, the next thing in the proof, I for some reason I skipped this line, is exactly solving the issue that I had. So good. Somebody has a solution to this problem. Okay, but does anybody know what the problem is? So remember, I wrote down this. This is actually maybe a little sneaky of me. I wrote down the limit as n goes to infinity of fn of x equals f. But that is for every fixed x, right? So what I've written down, we have a limit f, and we know that fn is converging to f, but pointwise. So we've only shown so far that f is the pointwise limit of f. We are not working with pointwise convergence, we're talking about convergence with this norm. So the issue is the pointwise convergence we have we found this limit f, which is a good candidate for the limit. It's the pointwise limit of the fn. But question, is it the norm limit of the fn? So this is like issue number 0. Issue number 0 is f the norm limit of fn? Okay. And there's one little line here in the proof where they prove it. So we're going to do a little claim. The claim is that the norm of fn minus f goes to 0 as n goes to infinity. So this is proving that not only is f the pointwise limit, but f is actually the norm limit of the fn's. And here's the proof that they do. So they say for every epsilon greater than 0, right, fn is a Cauchy sequence in norm. So find n so large, so norm of fn minus f of m less than epsilon, and this holds for all nm greater than n, which means the sup over all x of fn of x minus fm of x is less than epsilon. Yeah, they just took the limit as m goes to infinity. Okay, great. So I think what they did is they took the limit as m goes to infinity of this equation. So if this holds for all m greater than n, it holds in the limit that m goes to infinity. So this is what they're claiming in the textbook, which there's something about this that slightly bothers me, but maybe I'm just not looking at it enough. Okay. Yeah, okay, it's totally fine. I'm just being silly. Everything, so yeah, the thing that bothered me was they were kind of changing the limit. Now they're going to put the limit inside over here. So they're going to say that's the sup x of fn of x minus the limit as m goes to infinity of fm of x is less than epsilon. And that step of moving the limit in was bothering my brain, but I think it should be fine because all of these things are like continuous things. If it's true for the sup, then it's going to be true for every individual point. It's all legit. So you can, maybe if you wanted to be more careful, you would check this step. In the textbook, they do it in one line. They say just take the limit as m goes to infinity of this, you get that. And what is the limit as m goes to infinity of fm of x? That's the function f. Okay. So there you go. Okay, and that is the norm of fn minus f. So whatever the n worked for the Cauchy sequence will work to prove that fn is getting close to f. Okay. Questions or comments about this little issue that we just solved by reading the textbook? All right, so that was issue 0. Issue number 1 is now, so we have this limit, we know we're converging to it, but maybe it's not a continuous function. Like maybe you have a limit of these continuous functions, but they get like more and more vertical or something, and in the limit you have a jump. Could that happen? So the claim is that f is continuous. All right, and so here it's classic epsilon and delta land. Is f continuous? So given epsilon greater than 0, we must find delta greater than 0. Oh, and this is at every individual point x. So let's say given epsilon greater than 0, given x in 0, 1, and epsilon greater than 0, must find delta greater than 0. So x minus y less than delta implies f of x minus f of y less than epsilon. Classic definition. I guess very technically x should not be equal to y. Okay, so how are we going to do it? Well, here's how we're going to do it. F is close to Fn, right? We just proved that. F is close to the sequence Fn. The Fn's are continuous. And so we'll use the continuity of the function Fn to find our delta, and then we'll use the fact that Fn is close to F to prove that we're not making that much of an error. So here's how we're going to do it. So given epsilon greater than 0, use the continuity, and maybe before we use the continuity, let's use the fact that norm of Fn minus f goes to 0 to find, I'm going to call it n naught so large so that the norm of Fn naught minus f is less than epsilon by 3. So we're going to make an epsilon by 3 error by approximating f by Fn naught, and then we're going to find a delta that works within epsilon by 3 for Fn naught, and then we're going to use triangle inequality to paste the errors together, and we're going to have an error of no more than epsilon. So Fn naught minus f is no more than epsilon by 3. Use the continuity of Fn naught at x to find delta so that 0 less than x minus y less than delta implies fn naught of x minus fn naught of y is less than epsilon by 3. So basically, the function we want to prove is continuous, we're approximating it by the function fn naught, and we're using the continuity of fn naught. So we found our delta. So now, if you do f of x minus f of y, well, that is going to be less than f of x minus fn of x plus fn of x minus fn of y plus fn of y minus f of y. So we're bounding the difference by triangle inequality, I guess, with a less than or equal to. We're approximating f by fn. And again, these things are all bounded by epsilon by 3. So this is less than epsilon by 3 by the norm. So using norm of f minus fn less than epsilon by 3. And similarly for this guy at the end. So that thing's less than epsilon by 3. This thing's less than epsilon by 3 for the same reason. And the middle one is less than epsilon by 3 by continuity by the choice of delta. Epsilon by 3, this is by choice of delta. So the whole thing, 3 epsilons by 3 is epsilon. Okay. So there, f is continuous. So a uniform limit of continuous functions is still continuous. That was the proof. Okay. Questions or comments about that one? Classic epsilon by 3 argument. So I told you guys my favorite one-liner math joke, Bananach space. One of my favorite math comics is these 3 epsilons, and they are all standing around arguing with each other, and it's an epsilon by 3 argument. I will bring in the comic next class for you. Okay. Okay, so we're going to move on to the next thing that you can do with these complete spaces. And complete spaces, you can talk about the convergence of absolutely convergent series. So that's what we're going to do. So let me go to the spaces. Anybody still copying down? No? Okay. Let's so we can go to the overworld, and we're going to put in the definition 1.4.8, which is the definition of an absolutely convergent series. Now a series, you guys have seen series before of real numbers, so that's a sum, this kind of sum, summing from n equals 1 to infinity. And actually, let me make it k. So I'll use n in the top. So if you have some sum like this, you guys have talked about the convergence or non-convergence of sums of real numbers, but of course you can talk about the sum or non-convergence of any kind of vector, right? So as soon as you have addition, you can ask for the partial sums and do the limit. It's just like an R. So it's called absolutely convergent if, so I guess a series is called absolutely convergent. Okay, let's say an absolutely convergent series blank, how about this thing, is an absolutely convergent series. If what? Well, an absolutely convergent series in R of real numbers, you took the absolute value of each term and you added them together. In this one, we're going to take the norm. So we're going to do the sum, going from k equals 1 to infinity, of the norm of x, k, is less than infinity. So if you add up the norms, and that's some finite number, then we say it's an absolutely convergent series. Okay, and here is a fact, which is called theorem 1.4.9, which is that the space is complete, every Cauchy sequence converges, if and only if every absolutely convergent series converges. Right? So absolutely convergent means something about the norms, and being convergent means you converge as vectors, and these two things are exactly related by the same kind of Cauchy thing as before, right? So if you can measure the norms of the things, and those are convergent, then it will be a convergent series. This one actually has a nice picture proof. Let me show you the picture of this one as well. Okay, maybe not a picture proof, a picture argument, right? So what does the sum from k equal 1 to infinity of xk look like? So in the example I gave you, the picture example I gave you before, the xk's were the points, but now the points will not be the xk's, they'll be the partial sums. So let let Sn be the sum of the first k things. So that's k equals 1 to n of xk. And if you draw the sequence S1, S2, S3, S4, S5, then the vectors between them, those are the x's. So this is x. How did I do this? I guess you add on x2. And this one is x3. And this is x4. X5. So if somebody gives you a sequence of x's and you start adding them up, you should think of their vectors, and they're telling you the difference between the things, right? So you're adding up all these arrows, and you're seeing, like, where do you go? And what does absolutely convergent mean? It means that the sum of the lengths of all the arrows is some finite number, right? So absolutely convergent means the sum of arrow lengths is finite. So you add up all these arrows. If the length of all the arrows is not going to infinity, then, I mean, you're going to get some arrows, they're going to end up somewhere. That should converge, right? How could it possibly not converge? Well, the only way is, again, if you have a hole in your space, right? If you have a hole in your space and the arrows kind of like arrange themselves to point exactly to that hole, then it's not going to converge, but otherwise it's exactly the same. So that's the idea, and that's what I think of when I think of these partial sums. Okay, so yeah, we're going to prove the thing now, which is complete if and only if the absolutely convergent sequences work. And basically, the proof is converting from this picture to the picture we had before, right? Using s's and arrows to write out these like Cauchy things. All right, questions or comments before we jump into the proof? Okay, let's do it. So let's do one direction, which is we're going to prove claim yeah.
Is the Sn like vectors?
Yeah, the SNs are vectors too, right? So you should think of, when I draw these cartoons, I'm thinking of the vector space R2, right? And in R2, a point is a vector in R2, and then you can add a vector onto it and get another point in R2, and so on. So yeah, I guess vectors are both points and arrows, which is, I guess, a bit confusing, but yeah. Great question. Okay, so we're going to prove if it's complete, then absolutely convergent sequences converge. And we have the picture in front of us. What is the Cauchy sequence going to be? It's going to be the sequence Sn. So the claim, if it's complete, if space is complete, it's complete, and xn, or let's say the sum k equals 1 to n of xk is absolutely convergent, then limit as n goes to infinity of the sum from k equals 1 to n of xk exists. So if it's absolutely convergent and you're in a complete space, then the limit exists. And like the hint of how we're going to prove this, we have a complete space, we want to prove the limit exists. How do you prove that the limit exists in a complete space? You show that it's a Cauchy sequence. So the proof is we'll show the sum from k equals 1 to n of xk is Cauchy. Okay, we'll give that a name. Let's call that Sn, the sum of the first n terms. Why is this Cauchy? Well, Cauchy is all about the differences. The norm of, I'm going to leave a little space here, but we're going to fill in something, but what is Sn minus Sm? The norm, right? That's what Cauchy is all about. We're going to do some stuff here to pick an n that's big enough so that this will be bounded by epsilon. So let epsilon greater than 0. But what is the norm of Sn minus Sm? Well, Sn is the sum up to n, Sm is the sum up to m. So what do you get when you subtract them? You get all the things between n and m, right? So this is the sum k equals n plus 1 to m of xk. And now we're in business. The sum of these things by triangle inequality is less than the sum of the norms. So some finite sum, that's less than the sum of the norms of the xk's. Right, which is saying, in our picture, it's saying if you want to go from S1 to S5, you could not have gone further than if you add up the distances of all the arrows and add them together. Of course, you can go less because the arrows sort of like cancel out a little bit. are not perfectly collinear. But the worst thing you can do is go the distance of adding all the arrows together. Okay, and this sum is a finite sum, but not only is it a finite sum, it's almost like the tail of the sequence of the absolute values of xk. So this is even less than, I could sum this all the way up to infinity. I could go up to infinity of xk, right? And it's okay to go up to infinity because you told me it was an absolutely convergent sequence. So it's a convergent sequence, you add it up, that's going to be some tail. And now, by making n really big, if n is big enough, this will be less than epsilon. So why don't we say this is less than epsilon? And in the little space that I left, I'm going to say choose n so large, so that the sum from k equals n to infinity of the norm of xk is less than epsilon. And you could even say because it's convergent. It's a convergent series in R. All right, so we were assuming that it's an absolutely convergent series, which means this sequence is a convergent series in R. And then, for nm bigger than that m, we have this. So there you go. That's kind of like the logic of how we made the proof. Therefore, S is a Cauchy sequence, and Cauchy sequences converge because the space is complete, so the limit exists. Okay. That's one direction. Yeah?
Sorry, can you just explain the k equals n plus 1 again?
Like the first one?
Yeah.
Yeah, okay, this is great. So Sn, okay, yeah. You know what? It's important if n is bigger than m or not in the proof. Let's say m is bigger than n. So for m bigger than n, right? It's supposed to work for any two numbers, but one of the two numbers is always bigger than the other number. So let's just call the big one m. Let's call the big one n. And I should write, let me write Sm minus Sn like this. And right, so Sm is the sum going from I equals 1 to m, like 1 to 100, and then you subtract off 1 to 50. So what's left is everything from 51 to 100.
Okay.
So yeah, thank you for, I did have it, I think it was like maybe slightly wrong before. Now at least it's more clear. Thank you for that. Any other questions or comments? Okay, now let's do the other way. And again, it's all about forcing Cauchy sequences to appear. So the claim, the other direction. Yeah, if every absolutely convergent sequence converges, then the space is complete. If every absolutely convergent sequence converges, not sequence, series, then the space is complete. Okay, so how are we going to prove this? Well, someone is going to give us a Cauchy sequence. So xn, let xn be some Cauchy sequence. And we would like to show, we're going to fill in some stuff, and at the bottom of the page it's going to say, therefore xn is a convergent sequence, right? Here's the limit. Okay, we're going to find a limit for xn. How are we possibly going to find a limit for the xn? Well, we're going to have to manifest, we're going to have to make some kind of absolutely convergent series, and we were told that those converge, so we'll construct a convergent series, and then we'll find the limit of that thing, because we know that converges to something, and then we'll use that to find the limit of this guy, right? So we're given a Cauchy sequence, we're going to convert it into a series. So I would like to write that xn is equal to the sum of something. Right? Because if I can make these somethings, if I can make this an absolutely convergent series, then this limit will exist, and I'll have the limit of the xn's. So I would like this to be the sum, specifically something like k equals 1 to n of something sub k. Right? That's what I want to do. Can anyone think of a way to write just a plain old thing as a sum of other things? This is a really common trick in math. I guess in analysis, I don't know which part of math, but this is a common trick you've probably seen before. Yeah. An integral?
Sure.
Yeah, so let me think. I don't think it has anything to do with integrals. This is a good guess. Let me give a hint, which is a telescoping is the hint. Telescoping. Let me give one more letter. A telescoping sum. What is a telescoping sum? A telescoping sum is when you have a sum of things, but they just cancel themselves out to leave the first thing minus the last thing. And let me write it out for you, and then we'll see what the sum things are in a second. But xn, I can write it as something very silly. I can say it's x1 plus x2 minus x1 plus x3 minus x2 plus x4 minus x3 plus dot 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 plus xn minus 1. So it's a really silly way to write something as a sum of other things that you can always do. And the reason it works is because you got plus x2 over here cancels with the minus x2 over here. And then you got x1 cancels with the x1. And then if you do all the stuff, the only term that's left over is x. So this is called a telescoping sum. Let me erase these little marks. Who's seen a telescoping sum before? Okay. So that's what we're doing. So those are the sum things. Great. And not only is it the sum thing, so I'm going to write xn. It's the sum of x1, and then it's plus the sum k going from, I guess, 1 to n of xk minus 1. So there you go. Xn is the sum of things, and not only is it the sum of things, which is great, but it's the differences of elements, and we were told that it's a Cauchy sequence. So we actually know that the differences of elements can't be large, right? We even know that the norm of xk minus 1, that's like two adjacent elements, is eventually less than epsilon eventually. So like we're in good shape here. This is a good start. Question, yeah?
Would it have to be from k equals to 2 in order to get an x to 0?
That's a great point. I probably screwed that up. Let me see. Yes, I believe you. It is starting at 2. Okay. Yeah, okay. Okay, so these terms are getting small, like they're less than epsilon eventually. So we got good news. We got a couple things going for us. We got this telescoping sum. We got these things are small, but here is the problem. They are not small enough because we need the sequence to use the hypothesis of the problem. We need the sequence to be absolutely convergent, right? So it's not enough that these terms are less than epsilon, right? Basically, what I've pointed out for you is that the norm of xk minus 1 is going to 0. Maybe that's a better way to say it, right? So these things are getting small. Is getting small, they're going down to 0. Is that good enough for it to be absolutely convergent? No, it's not. Right? Because it could go down to 0, but not be summable. So problem could be that the sum of k equals 2 to infinity, say of norm of xk minus 1 is equal to infinity, right? So even though the individual vectors are getting close together, it's not enough. We need them to be summable. Going to 0 isn't good enough. So we need a way to rescue this argument. And so the telescoping sum that I wrote will not work. We need a way to make sure that not only is it going to 0, but it's going to 0 super fast enough that it is summable. And when it's summable, then it'll be an absolute convergent series. And then we will know it converges. Okay, so we need some argument here, or some idea to rescue the argument. Right now, it's not working. Anyone have any ideas what we could try? Let me give you a minute to think, and I'll give you a hint even. In the telescoping sum, I wrote down a telescoping sum, but there are actually many other telescoping sums that you can also use for xn. So if you can think of a more clever telescoping sum than the one that I used, so I did x1, then I did x2, then I did x3, then I did x4. Maybe there's a more clever telescoping sum you can use. Let me give you guys like 2 minutes to think, and then I'll reconvene. I'll show you my answer, and we'll see if anybody figured it out.
I have
Okay, time is almost up. The room is stony silent. Anyone have any ideas? So I heard you guys say something about one half, 1/3, 1/4. What was your idea with that?
Oh, I was just thinking about, you said it could be that sum goes to infinity.
Oh, okay, you were coming up with an
Trying to
example.
Figure out when.
Yes.
So,
Yes, this
that's
is
all that was.
this is right. Yeah. So I guess this is all resting on the stuff you guys did in, I guess, calculus 2 or calculus 3 about sums, right? So if it's something like 1/k, then that will go to 0, but the sum will be infinity. We need it to go to much faster than 1/k. And this is the start of the idea, is we're going to pick a sequence that we know converges, and we're going to force the terms to be less than that. And I have a favorite sequence, which is I'm going to force comparison. Okay, so all of this stuff is like battle land, like we're just thinking. Okay, but we're going to force a comparison to my favorite summable sequence. Of course, you can have other summable sequences, but this is the coolest one. It's the sequence 1/2 to the k, right? So I want to somehow make it so that the thing I look at, instead of being like just small, it's really small, and by really small, I mean it's going to be less than 1/2 to the k. And the reason that's nice is because if you sum that up, you get exactly 1. I guess I started at 2 now, so you're going to get a half. Okay, we're going to make it start at 1, because that's what I want. Okay, which is 1. So that's what the idea is. Like, you cannot let this thing just be some wild thing that's going to 0. You need to force it to be less than something you know is summable. And so we're going to force the thing here, the norm of the differences that we're looking at, that's going to be less than 1/2 to the k. And you might say, okay, but you have no way to know that that's less. There's no reason that xk minus 1 should be less than 1/2 to the k. But what we do know is that eventually, somewhere deep into the sequence, it's eventually going to be less than 1/2 to the k. So what I'm going to do is I'm going to build a new sequence by looking potentially very far into the sequence. I'm going to construct a subsequence, so that subsequence will be bounded by 1/2 to the k. So this is the idea. This is going to be the main idea, is I'm going to find a subsequence. I'm going to abandon doing 1, 2, 3, 4, and I'm instead going to do x sub pk minus x sub pk minus 1. And that will be bounded like this. So that's the idea. And written out as a thing, that's going to be like saying x 1,000, instead of writing 1,000 terms in my sequence, I'm only going to have like 10 terms. So maybe this will be x1 plus x10 minus x1 plus x100 minus x10 plus x 1,000 minus x 100. So before I did 1,000 terms, and I couldn't control how big they were. But by making the numbers big enough, by going to a subsequence, I have much fewer terms, and I can control how small the terms are. So that's the idea. And I'm going to use the Cauchy sequence to do this. So all of this stuff up to now is sort of like idea land, like thinking. I could have just given you the proof directly, which is what they do in the textbook, but now at least you see where it comes from a little bit. So what I'm going to do is I'm going to let epsilon equal 1/2 to the k, and then since the sequence is Cauchy, xn is Cauchy, there exists Pn, or Pk rather, Pk, so the norm of x, let's call it a minus xb, is less than 1/2 to the k for all ab greater than pk, greater than or equal to, right? That's the definition of Cauchy with epsilon equals 1/2 to the k. And I specifically chose this 1/2 to the k because it's summable, it's going to make everything work. So if you make the sequence pk like this, then in particular, the norm of x pk plus 1 minus x pk is less than or equal to 1/2 to the k, which is the kind of thing that I want. So I chose the pk's, and by choosing epsilon to be a summable sequence, I got this thing. And now I'm going to do the telescoping trick. And I'm going to write xpk is going to be x1 plus xp1 minus x1 plus xp2 minus xp1. Now it's a telescoping sequence, but only looking at these pk's. So xpk minus xpk minus 1. Or in other words, it's the sum x1 plus the sum of k going from, okay, I guess I should call this n. Let's call this n, and let's make this n times n minus 1 so that I can continue to use xpn minus xpn minus 1. So I can sum from k equals 1 to of xpk minus xpk minus 1. Okay. Oh, I guess this should be xp1. Okay, great. xp1. Okay, let's yeah, xp1, and then this one will be. We'll delete this one. Okay. Sorry for people trying to follow along in the notes. Math is messy. Okay. Here we go. Okay, so now it's like a legitimate thing. I'm just doing the trick that I did before with this telescoping, but I'm not counting every single term. I'm only looking along the sequence where I can control that things from the sequence are, not only are they going to 0, but they're going to 0 so fast that they're summable. And you might have to take some insanely huge numbers, right? Like you might have to skip forward by billions in your sequence, but that's okay, we can do that. Okay, and now it will work. This sequence is absolutely summable. But the sequence is absolutely summable. So the sum from k equals 1 to infinity of norm of x pk minus x pk minus 1 is less than or equal to the sum from k equals 1 to infinity of 1 over 2 to the k, which is 1, which is less than infinity, famously. So it's an absolutely convergent sequence. An absolutely convergent series, rather. Okay. So that's absolutely convergent series, and by the hypothesis of the problem, we said every absolutely convergent series converges. So therefore, the limit as n goes to infinity of xpn exists, and we can say because we are given all absolutely convergent series converge, are convergent. Okay, so there we go. The limit exists. Am I done? Is that what we wanted to show? No. Yeah, we're very close, but we're not quite done. What is missing? Yeah.
Prove that x in itself actually converges.
Exactly. So we've gotten this special subsequence, and that was like crucial, right? We proved it that the special subsequence, we found it, the special subsequence like made our life a joy because it was summable, and we've proven that that special subsequence converges. Okay, but could it be that the entire sequence diverges, but only the special subsequence converges? So now we got to prove that the whole thing converges. Well, fortunately, the whole sequence we were told is Cauchy, so that means the points are close together. So all the points are going to be close to this subsequence because it's a Cauchy sequence. So last step, let's prove that the limit as n goes to infinity of xn exists, and let's give this thing a name. Let's call the limit, let's call it x is equal to x2. And how can we do that? Well, the points are all getting close together, so we'll just wait until this xpn, we'll wait until that's within epsilon of x, and then all the other points will be within epsilon of xpn, and then the whole thing will be within epsilon over 2 epsilon of x, right? So the pn's are getting close to x, all the other points get close to the pn's because it's Cauchy, so by triangle inequality, they all get close to x. Let's do it. So given any epsilon greater than 0, find n, so the norm of xpn minus x is less than epsilon, and actually we know we're going to be combining two things, right? This guy will be close to that, and these guys will be close to that guy, so why don't I make it an epsilon by 2, and this will work for all n greater than n, and let's make this a lowercase n. Okay, so the xpn's are converging to x, so they get within epsilon 2 of the x. Since xn is Cauchy, find, let's call it capital M, so x m minus x pn is less than epsilon 2 for all m greater than m. Okay, so this one is not exactly right. I switched out a pn here, right? But pn is a subsequence that goes to infinity, so the Cauchy property, right, will work. Eventually, there's some number that you're larger than. Just wait till n is big enough, right? So n is bigger than n. I guess you might need to possibly increase n. Okay, let's call this n1. Let's call this one n2, and N2. Okay, so the PNs are getting close to the X's, the XMs are getting close to the XPNs. So then, for M bigger than M. Okay, I just realized I'm making this more complicated than I need to be. I really don't need this for all, but we can just pick an example. Why don't we do this? For M bigger than N, we'll do the norm of X minus the norm of XP, and we'll do the maximum of N1, N2. That's not what I want. I want XM on this side. That's going to be on the right-hand side. Minus XM. That's going to be less than or equal to X minus XP max of N1, N2. So we just pick some example with an X. Okay, there we go. Plus XP max N1, N2 minus XM. And both of those things are less than epsilon by 2. Okay, less than epsilon by 2 plus epsilon by 2, which is epsilon. Okay, so again, maybe this is one where a picture proof would help. If it's converging along some subsequence and it's Cauchy, then everything has to converge. All right. Okay, that got messier than I was expecting. Any questions or comments about that one? All right, yeah, maybe I should, this could be like an exercise. We just proved this exercise, by the way, that if xn is Cauchy and xpn is a subsequence with the limit as n goes to infinity of xpn equals x, then the limit as n goes to infinity of xn equals x2. Actually, I think there's a really nice exercise that I put on the list of extra problems on homework 1, which is this one. Let me say this one. Here's another one. If xn is a sequence with the following property, such that what? Such that every subsequence xpn has a subsequence xpnk that converges. Okay, so that's a property. So xn, if xn is a sequence with this property, every subsequence has a convergent subsequence. Subsequences have this property, some sequences don't have this property. But if xn is a sequence that has this property, then limit as n goes to infinity of xn exists. It's convergent as well. This is a fun exercise. And I believe the one we just proved is an easier version of this one. So that's a good one. If you want to play with your sequences and see if you're understanding, that's a good one to try. Okay. How did we get here? I think the answer is I'm getting tired. Okay. Any questions or comments about this stuff? Anything so far? Yeah.
Is the epsilon over 2 because of its Cauchy sequence?
Yeah, so this epsilon over 2 was because the PNs were converging to X. And this epsilon over 2 is because it was Cauchy. So we had like two inputs, right? We had one was that the limit of the XPNs are X, and the other input is that because it was Cauchy. So that's because it was Cauchy, and this is because the limit exists. So yeah, we're combining the two things. They're all getting close together, and XPNs are getting close to X. Yeah?
For the argument highlighted in green right now,
Yes.
are we sort of selecting an M and then finding N such that Pn is greater
Yeah,
than
exactly.
N?
Yeah, right. So if you wanted to be very pedantic about it, you could say, find the N, then find the M so that the PM is big enough, like past the N that you found. But yeah, that's it in one line. Yeah. Okay. I'm pretty sure in the textbook they just say like, obviously, and then they write down. You guys should read the textbook. Okay. All right. I try to make the math like a little more real in the class, like we're actually fighting a beast, because that's what we're doing. But like written down, when you write down math, people often don't write down. I got another good comment for that. I'll bring that in next time too. Okay. Any other questions? Okay, I'm gonna leave you guys with one question, and this will lead into the next chapter of the book, which is exercise 2. Exercise 2. So I proved for you that the space C01 was a complete space, and then we did more stuff about Cauchy sequences. Basically, if your space is not complete, then you suck. Like you just have these holes, you like can't do anything, right? Like you can't do limits. You don't know if your limits exist or not. You can't do infinite series. Nothing works. So here's the question for you. Is the space L1, so the space of functions on 0, 1 with the L1 norm, integral of the absolute value, is that complete or not? And as always with the questions, I want you to think about it. You're not going to know the answer. You're basically going to have to guess. And I gave you some options. Okay, so take 2 minutes and tell me what you think. Maybe you only need 1 minute. Let's just give you 1 minute in the interest of time. Okay, put in your guesses. Is the space L1 complete? If you have a sequence of functions that are converging in L1. If you have a Cauchy sequence in L1, is it convergent, right? Is it complete? Does every Cauchy sequence converge? Okay. And the answer is, well, what did you guys say? You said, it depends. You guys know me too well. Of course it does depend. What does it depend on? Does anyone know? What could it depend on? Is there anything ambiguous in the question? Yeah.
The usual incongruity.
That is a great idea. It is not to do with continuity. So it is not to do with continuity. This is not a question about continuity. There's another slippery thing inside this little box of symbols that is the thing it depends on. And so there is a certain way to interpret this where the answer is no. There is a certain way to interpret this, and the answer is yes. And this is a very, what were you going to say? The absolute value? Well, the absolute value is okay. Let's go through the symbols that are here. Absolute value is totally legit. There's no slippery stuff with absolute value. Integrating from 0 to 1, those are the bounds, 0 to 1. That's totally fine. Yeah, what do you think?
Oh, I was going to say, is it integrability?
Yeah, it has to do with integrability. So it's this integral sign. What do we mean when we say integral sign? Well, the integral you guys have been taught so far is the Riemann integral. Okay? And if you do this with the Riemann integral, if the like funny S thing means Riemann integral, then the answer is no. The answer is no. But you guys are going to learn about a new integral called the Lebesgue integral, and that integral is better, and when you do the Lebesgue integral, the answer will be yes. Okay? So let me give you the one example. This will be the last thing we do today, which is the reason the Riemann integral is not good enough for what we want to do. So Riemann integral does not respect limits. It does not respect limits. So this is the problem with the Riemann integral, is that in the Riemann integral, it's not complete. You're going to have sequences that you want to converge. They're going to be Cauchy, and there's going to be no limit that works anytime you're using the Riemann integral. So e.g., Fn is Cauchy in some norm, but the limit as n goes to infinity of Fn won't even be Riemann integrable. Won't be Riemann integrable. And there's one very classical example of this. Here is the big example, which is the function f of x, which is 1 if x is rational, if x is in Q, and 0 if x is irrational. Okay, so this function, some people call this the salt and pepper function, which I love that name. So here's a picture of the function. right? What does it look like? Well, it's 1 at every rational. So every time there's a rational number, I draw a dot at 1, right? These are all the rationals. And then every time it's irrational, I draw a dot at 0, which is down there. So if you're going to plot this function, you kind of have a salt line at 1 and a pepper line at 0. But the rationals and the irrationals are both dense. So you're kind of drawing like dots everywhere, right? So this is dense, and this is dense. Okay, and this function is famously not Riemann integrable. You cannot do the Riemann integral of this function. It's not that the Riemann integral is infinity or something. It's like there's no way to make sense of the Riemann integral. And the reason is, how do you do the Riemann integral? Well, you cut really narrow rectangles, and then you hope that as the rectangles get more and more narrow, it converges to something. But in this function, because it's dense at 1 and it's dense at 0, no matter how thin you make the rectangle, you never make any progress. It always has some points where it's 1, it always has some points where it's 0. And so the upper, if you want to get into the lore of the definition of the Riemann integral, the upper Riemann sum is always 1, and the lower Riemann sum is always 0. Equals 0 always, and this is 0 always. Right? And the definition of the Riemann integral is you take the limit as the upper Riemann sums and the lower Riemann sums. They converge to something, and we call that something the Riemann integral. Right? And in this case, they're not converging. One of them is always 1, one of them is always 0, and it's not converging. Okay, and that wasn't a big problem before. We're like, okay, some functions are not integrable. But the real issue is that we don't respect limits. So I'm going to write down a sequence of functions that converges to the function f, and those functions are integrable. So here's my sequence of functions. Fn of x is going to be 1, not for every rational, but just for a list of the first n rationals. So q1, q2, all the way up to qn. And 0 if x, let's say otherwise. Okay, so fn is a function. It's like the salt and pepper function, but it's like a baby salt and pepper function. It has exactly n ones, right? So there's n ones. And then the rest is all 0. It's like honestly 0 in between these little spikes. I'm going to call it mostly 0. Mostly 0. So fn is converging to f. And it's converging pointwise. And like you can make sense of the integral of f. In fact, the integral of f is always 0. From 0 to 1, dx is always 0 for all n. The reason it's 0 is because anytime you have a little spike, you trap a really, really narrow rectangle around the spike, and as the width of the rectangle goes to 0, that little spot, one little dot of having it be equal to 1, doesn't contribute anything to the integral in the limit. So this integral is 0. So this is like the fundamental problem. The Riemann integral does not respect limits. We have a bunch of functions that are going to this other function, they're converging, but these ones are integrable, and that one is not. And the Riemann integral just does not respect that, and you can't do limits. If you try to make sense of the space L1 with the Riemann integral, it's not a complete space, and like everything falls apart. Like what was the major problem we said we would try to do in the course? We said we would try to do Fourier series, right? So if you're doing fn of x is the sum of alpha n times the cosine of nx, summing from n equals 1 to, let's call this m. Right? This was the kind of sum that we were doing. You cannot know if the limit exists. So even if the alpha n's are summable, like you don't know if these limits exist because in the Riemann integral, it doesn't respect limits. So what are we going to do in the rest of the course? We're basically done chapter 1. Next class, we're going to start chapter 2, and chapter 2 is all about defining the Lebesgue integral. So new integral, which is the Lebesgue integral, and the whole point is when you use the Lebesgue integral, it will respect limits. Okay? So when you do the Lebesgue integral, this space will be a complete space. All the Cauchy sequences will converge, and so, for example, the nasty function I gave you over here, even though this function is not Riemann integral, it is Lebesgue integral, and the integral of this function is 0. So it respects the limit. 0, 0, 0 over here, that one is integrable, and the integral is 0. So that's what we're going to do. And so yeah, there's a long chapter, chapter 2, defining the Lebesgue integral and doing properties with it. And that's going to set up our space. And then we're going to study this L1 and L2 spaces and learn how Fourier series work from there. Okay, have a great weekend, and see you guys on Tuesday.